Usually when you think about artificial intelligence, there's this expectation of just like flawless consistency,
Oh,
right?
yeah, absolutely. You
Yeah.
expect a machine to be a machine.
Right, like a calculator, you type in some massive complex equation, and it doesn't matter how long it is, the machine just crunches the numbers and spits out the absolute truth.
Hmm.
But then, you sit down to have a multi-turn conversation with one of today's state-of-the-art language models, and these are systems that have essentially read the entire internet.
Right, they know practically everything.
Exactly. But suddenly, that perfect calculator acts a lot more like a forgetful goldfish.
Yeah, it's really jarring.
It is. You find yourself looking at this cognitive landscape that is just completely baffling, which is why today's custom-tailored deep dive is focused on uncovering why these incredibly powerful systems still make, well, wildly embarrassing logical mistakes in really simple conversation.
It's a huge problem in the field right now.
Yeah, and we are pulling from a fascinating new paper to figure it out. It's by Google DeepMind researchers Michael C. Moser, Shoaib Ahmed Siddiqui, and Roseanne Liu, and it's titled The Topological Trouble with Transformers.
It's a great paper, really eye-opening.
So we are going to explore how a structural flaw in the actual physical shape of modern AI is forcing researchers to completely rethink how these systems think. And I think the craziest part of their proposed solution is that fixing AI might actually involve teaching it how to have an unconscious mind.
Yeah, I mean, applying the concept of an unconscious mind to a machine, it sounds a bit like science fiction.
Totally.
But it actually addresses a very real mechanical deficit. Though before we get to the solution, we kind of have to isolate the specific cognitive skill that current AI lacks.
Right.
In computer science and cognitive psychology, this missing skill is known as state tracking.
Okay, let's define that for the listener because it sounds like one of those terms that gets thrown around a lot in tech spaces. What exactly is state tracking? And how does it differ from what a massive language model is already doing when it, answers a question?
Sure. So state tracking is the ability to iteratively update latent variables as an environment or a conversation evolves.
Okay, what does that mean in plain English?
Well, think of it as maintaining a working belief state. Like when you're in a situation, you have underlying hidden assumptions about reality. Those are your latent variables.
Right.
As new information comes in, you update your internal model of the world. You hold on to that updated reality, and you use it to interpret the very next piece of information.
So it's basically keeping a running tally of the changing reality of a situation.
Exactly. It's a running tally. And that running tally is fundamentally different from a transformer model's native superpower.
Because transformers are the architecture behind almost all modern large language models, right?
Right. And they're built for retrieval.
Mm-hmm.
They have these massive context windows, meaning they can look back at thousands of words of static text and pull out exactly what they need.
Mm-hmm.
But retrieving a fact from a giant wall of past text is completely different from dynamically tracking a changing state in the present moment.
Yeah, and the DeepMind paper highlights this hilarious but also genuinely a concerning example of this failure using the game 20 questions.
Oh, yeah, the guessing game example. It perfectly illustrates the problem.
Right, so user tells the AI, think of a number between 1 and 100, and I'll guess. Just say higher or lower. The user guesses 60. The model says lower.
So the secret number has to be less than 60.
Exactly. Then the user guesses 50. The model says lower. Okay, the number is less than 50. Then the user guesses 51, and the model responds higher.
Which is just, it breaks the foundational logic of the entire game. Right, because if the belief state was properly updated, meaning the AI knows the target number is less than 50, it is mathematically impossible for it to be higher than 51. The model just completely lost track of the valid range.
It's so weird.
And the researchers highlight an even more revealing failure using Gemini 3. They specifically tested its thinking mode, where the model explicitly writes out its internal thought process.
Oh, right, where you can see its scratchpad.
Exactly. So the model notes in its scratchpad, I have internally selected the hidden number, choosing 42. The user guesses 60. The model correctly says lower.
Makes sense so far.
Right. But then the user guesses exactly 42, and the model responds lower.
Oh my gosh. It's like having a conversation with a friend who has this flawless photographic memory of every single syllable you just uttered, but has absolutely zero comprehension of the actual plot of the story.
That is exactly what it's like.
They can quote the transcript back to you verbatim, but they don't understand the causal reality behind the words.
That analogy captures the frustration perfectly. And This limitation extends far beyond parlor games.
Right, because it matters for real-world applications.
Exactly. When an AI fails at state tracking, it loses coherence in long conversations. It fails at complex information-gathering tasks because it forgets what it has already ruled out.
Mm-hmm.
It completely breaks down when trying to cooperate with other AI agents. I mean, if a system cannot reliably track the evolving state of the world, it cannot function as a reliable collaborator for you.
So if these models are trained on literally all human knowledge and have hundreds of billions of parameters, why do they fail at a task a 5-year-old can do?
Well, the researchers argue the answer lies in the AI's physical architecture. Its topology.
Topology. Okay, break that down for us.
This brings us to the core of the problem.
Yeah.
Transformers are feed-forward models. To visualize this, imagine a grid.
Okay, picture a grid.
The horizontal axis represents time, mapping the sequence of words coming into the model one by one. The vertical axis represents the physical layers of the neural network, starting from shallow layers at the bottom and stacking up to deep layers at the top.
Okay, so a grid moving left to right for words and bottom to top for depth. Got it.
Right. In a feed-forward transformer, activation, the flow of electrical signals and information, only moves upwards and to the right.
Just up and right.
Exactly. From shallow to deep and from past to present. The critical limitation here is that information never flows backward, and it never loops around in a circle.
It's a strict one-way street.
Precisely. Because of that one-way street, integrating a new piece of state information pushes that realization deeper and deeper into the network stack.
Wait, what do you mean by that?
Well, if you update your belief state at word number 1, that processing happens, say, in layer 2. At word number 2, you update the state again, which happens up in layer 3.
Oh.
Yeah, with every single input step, the evolving representation of reality is pushed higher up the layer stack. Eventually, the model literally runs out of vertical depth.
Wow.
The information hits the ceiling and becomes totally inaccessible to the bottom of the network.
To make this abstract topology concrete, the paper uses a really brilliant example about a guy named Fred.
Oh, the bank example, yes.
Right. So the sentence is, Fred takes the day off work, pulls out his fishing pole, and drives to the bank.
This is a classic polysemous word problem, a word with multiple meanings. Because bank can mean a financial institution or the muddy side of a river.
Yeah, and using an investigative technique called patch scopes, researchers were actually able to peer inside the individual layers of the AI while it processed that specific sentence.
It's fascinating what they found.
It really is. Deep in the network up around layer 6, the model correctly analyzes the context clues like fishing pole and deduces, Fred is at a riverbank.
Right. But the fatal flaw is that this accurate realization only exists at layer 6 and above.
So when the user asks a follow-up question, is it likely that Fred will find an ATM at this bank? The AI confidently replies, yes, most riverbanks have ATMs on site for customer convenience.
Exactly. It hallucinates a completely nonsensical scenario.
It's so funny, but also kind of baffling.
Well, understanding the feed-forward topology explains the mechanics of that hallucination, because the deep layers figured out it was a river. But when the new word ATM comes into the model, it doesn't enter at layer 6.
Right, it enters at the bottom.
Yes, at layer 1. Those shallow layers are completely cut off from the realization that happened above them. They just see the word bank next to the word ATM and make the superficial statistical association that banks have money machines.
Okay, let me try mapping this onto an analogy for you. Imagine an automobile assembly line.
Okay.
The workers at the very end of the line, representing the deep layers, have looked at the pieces and figured out they are building a boat today. But the workers at the beginning of the line, the shallow layers, are still blindly throwing car parts onto the conveyor belt because the communication only flows one way. They can't shout back down the line to say, hey, stop sending steering wheels, we're doing boats.
That visualizes the disconnect perfectly. High-level disambiguation is completely isolated from the shallower layers processing the subsequent words.
I have to push back here, though.
Sure.
If the shallow layers are flying blind on a one-way street, how do current foundation models work at all? I mean, I use these models daily to code, to write, to brainstorm. If the architecture is fundamentally broken for tracking reality, how are they fooling us so convincingly?
They are fooling us through incredibly clever brute force workarounds. Because transformers have that massive context window, the perfect photographic memory of the conversation transcript, they transform state tracking problems into working memory problems.
Okay, how so?
The paper gives a highly technical example involving parity to illustrate this.
Okay, how does the parity example work?
Imagine feeding the model a long sequence of zeros and ones and asking it to determine if there is an even or odd number of ones.
Simple enough?
Right. An ideal logical system would just keep a running tally as it reads each number, updating a single state from even to odd to even. But as we established, a feed-forward transformer can't easily maintain a looping tally.
Because it's a one-way street.
Exactly. Instead, it computes the answer from scratch using its vertical depth. In layer 1, it compares neighboring pairs of numbers. In layer 2, it compares pairs of those pairs, creating 4-bit chunks. In layer 3, it evaluates 8-bit chunks.
Wow, so it's doing all this extra work.
It achieves the final answer by crunching the entire sequence simultaneously, basically faking a running tally through massive parallel computation.
That sounds incredibly computationally expensive for something that should just be a simple counter.
Oh, it is. Hugely expensive.
I guess that explains the recent explosion of chain of thought prompting. Right?
Yes, absolutely.
This is when you ask a model a complex question, and it spits out a huge block of text labeled thinking before it actually gives you the answer. The DeepMind authors call this a cop-out for state tracking.
It is an artificial patch for the architectural flaw. Since the shallow layers can't access the deep realizations, chain of thought forces the model to print its deep, complex representations out as actual text.
Oh, I see.
Right. Once that realization is printed as a word in the transcript, it enters the context window. And because it's in the context window, it feeds back into the bottom of the model at layer 1 for the next step.
So the model is manually routing the deep insight back to the start of the assembly line by writing it down.
Exactly.
That is fascinating. Chain of thought is basically the AI talking to itself out loud to compensate for its amnesia.
Yeah, that's exactly what it's doing.
And humans do that too. I mean, if I'm trying to solve a really complex calculus problem, I write down my intermediate steps. I might even mutter to myself to keep track of the complex logic.
We absolutely rely on explicit thought traces for complex reasoning.
But the limitation is that it's deeply inefficient for everyday reality. If you and I are having a conversation, I don't need to constantly mutter to myself out loud, remember, this is my friend, we are talking about a deep dive, I should use English.
Right. You just know.
Yeah, I shouldn't need a paragraph of explicit thought to remember that bank means river in the context of a fishing trip.
And researchers term this implicit understanding microcognition.
Microcognition.
Yeah, it is the mundane, moment-to-moment state tracking that human beings execute automatically and unconsciously. We just absorb the context. Relying on explicit thought, traces like making the model write out a paragraph just to track the setting of a story wastes the context window, burns massive computational power, and ultimately prevents the model from achieving true fluidity.
So if we can't keep patching the problem by forcing the machine to think out loud, how do we actually fix the core architecture? The proposed solution feels a bit like going back in time.
It really does.
We need to revive a concept that predates the transformer entirely.
The fix requires a return to recurrence. Recurrent neural networks, or RNNs, were the dominant architecture in AI before transformers took over.
Right.
Unlike the strict one-way street of a feed-forward network, recurrent architectures allow for cyclical communication. Information is permitted to loop back on itself.
Okay, so it can look back.
In mathematical terms, a state at time t is a function of the state at time t minus 1 plus the new input. It provides a dedicated mechanism for true dynamic state updating.
But wait, we abandoned RNNs for a reason. They were notoriously difficult to train, they were slow, and they suffered from catastrophic forgetting, where they would lose track of information over long distances anyway. We can't just throw away the transformer and go back to 2015.
That is the crucial tension here. The goal isn't to replace the transformer. The goal is to weave recurrence directly into it.
Ah, okay. A hybrid.
Exactly. The researchers provide a taxonomy for how to unroll a recurrent transformer, mapping the new hybrid architectures across 3 distinct dimensions.
Let's break down those dimensions so we can visualize how these new hybrids actually operate.
Sure. First, you have the vertical dimension, the layers moving bottom to top. Second, you have the horizontal dimension, the input steps moving left to right as words enter.
Okay, depth and time.
Right. And third, you have the autoregressive dimension. Autoregressive simply refers to the way a model generates the next word based on the previous words, how it steps forward in time during execution.
So how are engineers manipulating those 3 dimensions to build better state tracking?
Well, along the vertical depth axis, we are seeing what are called looped transformers.
Looped transformers.
Yeah. Instead of information traveling up and immediately exiting, an engineer might take a specific layer block and mandate that the information loop through it multiple times, refining the state before it is allowed to travel higher.
Interesting. And what about the horizontal axis, the input steps?
That is where state-space models like MBA operate.
Yeah.
MBA allows information to flow horizontally from one input step directly to the next input step within the exact same layer.
Wait, so they don't have to go all the way to the top first?
Exactly. The shallow layers are finally allowed to communicate with each other horizontally, passing a hidden state along the sequence without needing to push it up to the deep layers first.
So returning to our assembly line metaphor, instead of the front workers being totally isolated from the back, imagine a system where a master blueprint, the hidden state, travels down the conveyor belt alongside the car parts.
Right.
Every worker at every single station can read the blueprint, update it based on the part they just installed, and pass the updated blueprint to the very next worker.
A vastly more accurate metaphor, yes. The state is maintained and passed along locally.
That makes a lot of sense.
And then the most fascinating category emerges when you combine the depth axis with the autoregressive axis, creating what are called latent thought models.
How do latent thought models function?
Well, in a standard model, you input the word bank, and it immediately pushes through the layers to predict the next word. In a latent thought model, multiple internal steps happen for every single input token.
For every single word.
Yeah. The model receives the word bank and holds it. It churns its internal state once, perhaps realizing it's a financial institution. It churns a second time, factoring in the fishing bowl, and updates the state to river.
Wow.
It might churn a third time to solidify that context. Only after dynamically evolving that internal state multiple times does it finally generate the next word.
That completely changes the paradigm. But there's a glaring bottleneck here, isn't there?
There is.
I mean, transformers conquered the world because they processed data in parallel. They read the whole book at once during training. Recurrence is inherently sequential. You can't process page 2 until you know the hidden state of page 1. Does introducing recurrence mean we lose the incredible speed that makes massive AI possible?
Balancing that trade-off is the central challenge of the next generation of AI. The Google DeepMind paper doesn't just diagnose the problem, though. It outlines a roadmap of highly promising directions to build an architecture that has both the parallel speed of a transformer and the state-tracking fluidity of a recurrent model.
Let's look at that roadmap then. If tweaking the physical architecture slows everything down, are researchers finding ways to thread the needle?
They are. One major approach focuses on enhanced architecture. The paper highlights experimental models like RWKV7 and path attention.
Yet, what do those do?
These architectures are mathematically designed to permit parallel processing during the training phase, so they remain fast to build while possessing the structural expressivity required to execute sequential state updates when you actually use them.
But if overhauling the core math is too difficult, is there a way to just, cheat the training process? Can we force a feedforward model to act like a recurrent one?
Yes, actually. The second approach is approximating state tracking. You keep the fast one-way architecture, but you design highly specialized training objectives.
How does that work?
You essentially bombard the model with specific penalties and rewards during training, coercing it to internally mimic state tracking.
That's clever. What if we tackle the computation problem by just doing less of it? I mean, humans don't consciously update our state of reality with every single syllable someone speaks.
That mirrors the third direction,
Yeah.
coarse recurrence. Instead of updating the recurrent state token by token, which burns immense compute, you chunk the updates.
Chunking, right.
The model might process an entire sentence rapidly in parallel and only update its recurrent state at the period. Updating at the boundary of a complete thought saves massive computational overhead.
That aligns perfectly with human cognition. We process ideas in chunks. What about the internal wiring of the models themselves?
The fourth direction involves leveraging representational alignment, specifically focusing on residual connections.
Residual connections.
Yeah, in a neural network, a residual connection acts like a bypass lane on a highway. It allows information to skip the heavy processing toll booths of certain layers and travel cleanly up the network.
Oh, that's really useful.
The paper suggests that by training the model to use these bypass lanes more effectively, the different layers can align their representations, allowing the deep realizations to communicate across the network more naturally.
And the final piece of the roadmap seems to offer the most pragmatic compromise for the industry right now.
It really does. It focuses on efficient training pipelines.
Yeah.
Because recurrent models are punishingly slow to train from scratch, the suggestion is a hybrid life cycle.
So you mix them.
Right. You pre-train a massive feed-forward model Using standard, lightning-fast parallel processing, it absorbs all of human knowledge quickly. Then, only in the final stages of the training process do you graft on the recurrent mechanisms.
You acquire the broad knowledge base efficiently, and then you bolt on the dynamic state tracking engine at the finish line.
Exactly.
Which brings us to the ultimate question. What does this topological evolution mean for you, the listener? Why should you care about latent variables, residual highway bypasses, or whether an AI uses a feedforward or recurrent architecture?
Well, it changes everything about how we use these tools.
Right. It comes down to the difference between interacting with a highly sophisticated search engine and collaborating with a truly reliable entity. If researchers successfully integrate fluid state tracking, AI will stop acting like a forgetful goldfish.
Hmm.
It will be able to maintain deep, unwavering coherence across multi-day conversations. It will gather complex information over weeks without losing the plot, and it will operate seamlessly alongside other software agents without suddenly hallucinating that a muddy riverbank is a great place to withdraw cash.
By transitioning away from verbose, explicit chain-of-thought workarounds and embracing implicit recurrent activation dynamics, we are bridging the gap between the rigid math of modern AI and the fluid nature of human cognition.
We are essentially watching the architecture of artificial intelligence evolve an implicit working subconscious. It won't need to talk to itself to understand the reality of the room it is in.
This evolution, however, introduces a rather profound paradox regarding transparency.
Oh,
How so? Currently, when an AI relies on chain of thought, we can read its mind. We can literally look at the printed output tokens and audit the exact step-by-step logic it used to arrive at a decision. We can see the math on the page.
right. It's all right there.
But if the future of artificial intelligence involves shifting cognition away from explicit thought traces and into implicit, unobservable activation dynamics, an unconscious mind looping through complex hidden states, will we lose our ability to read their minds?
Oh, wow.
As these systems become vastly more capable of tracking reality, will we lose the ability to peek into their context windows and audit the logic of their decisions? We're trading transparency for capability, returning to the ultimate black box problem, just as the models become truly capable of reasoning.
That is certainly something to chew on as we watch these models evolve. Thank you for joining us on this custom-tailored deep dive. As always, keep questioning the architecture of the information around you, and remember, just because something has a perfect memory doesn't mean it actually understands the story. We'll catch you on the next deep dive.